Thank you very much. It's a pleasure to be here. Very exciting to share some of the way that we think about working on design in a different way. Really trying to bring a higher quality product for designing housing into the world and making way to do that by thinking differently about how we design and deliver that material. So I will start by giving a little context about, at least in the United States, where we are. There's a very large mismatch in the United States between how much housing is available and how much there is to be lived in. In addition to that, there's now a growing call from both regulators and also capital to really improve the carbon footprint of projects. And this is no news in Europe, but in the United States, this is actually new and actually growing in popularity, and that is really fueling a new way of thinking about the world. Also in the United States, the building codes are changing. Actually, they're becoming much more amenable to this kind of thinking about the world in a way that makes a big difference. And so we really wanted to take advantage of this as we set out to think this differently. But especially in the United States, and I think also around the world, the industry is really not set up for research and development, for thinking about new ways of doing the work. It's really a project-by-project implementation by, especially in the United States, developers. It's very transactional. And as a result, the practices are very old and almost ancient in the way that the business is handled. And so really we're trying to think of a new way of bringing projects into the world. So the way we think about this is what we call productization. And what we're thinking of is a way of trying to create a more repeatable, a more scalable delivery method for especially housing, which has many, many parts that can be leveraged and repeated and scaled. So productization actually enables the idea of moving much faster, improving the speed of the projects, much more precision in how we think about what we know about that project, what is the data that is available at early stages, lowering the risk to a developer, which is very important, especially in the United States, because it's very much risk-based, fixing and improving on the cost of the projects, and also removing variability, which causes that risk, which actually slows down the projects. And so we started thinking about how products are actually brought into the world outside of the built environment. And what is the process that happens in consumer electronics, in other products that you might find in the world. And so the process is very common, but it's just not common in the built environment. What that process involves with is the first thing is identifying the problem, and we've done that already today, and then defining that problem, understanding what the requirements are. And this is a really foreign step for most building projects. A program is usually set and understanding the areas and square footages, but it's very rare that one publishes a requirements document before a building project starts going. And then this idea of prototyping and designing something that is actually tested before it's put out into the world. That happens sometimes in a very small scale for large-scale projects, but it doesn't happen enough. It doesn't happen where you could actually try something different, test it out, and not have to risk the actual project for its results. So you don't worry about failing. Actually, you try to see if you can push the envelope. Next is this idea of validating and really questioning and testing and understanding whether it's actually making progress or not. And then lastly, once you feel comfortable, actually going into production into the world. Now, once you go into production, it means you're going to put a building into the world, for example. If you're in a series of projects, which is like a programmatic relationship, you might be able to then iterate over time and then continuously improve on a version 2, version 3, version 4, and have a feedback loop, which would allow you to then learn and get better at what you're doing and improve on that. Now, some of this process is something like what you might do in certain industries, like hospitality or retail, for example, where you're able to actually learn lessons and apply them back over and over again and continuously get better. But something like housing, it happens very rarely. And so we wanted to bring this idea, this way of working into the world. So what we do at Juno is we think about breaking this process down into a couple steps. So our tactics for how we work, number one, We think that if you have an aspirational product, that it will be more okay to repeat that over and over again in the world. We see this in consumer electronics, in phones, in cars, et cetera, where repeatability is fairly common, but we don't see it in the built environment. And I think it starts by saying, well, if you have something that people really want, that they really see the quality in, then you have the ability potentially to leverage that. So number one, it starts with this idea of building a building that warrants to be repeatable. Then we decide to break down that system of parts into what we call components, into repeatable pieces that are then organized based on either the use or the supply chain or the technology. Depending on the project, it could be very different. Then once we have these component parts, we then leverage tools and technologies to reduce the friction of using those parts over and over again and take away the brute force effort of making the building and using technology to replace that. Third, we then try to integrate as much as possible asset-light manufacturing, industrialized construction processes, where we can take advantage of controlled environments off-site, flat-packed means of shipping to the job site to reduce transportation and waste, and bringing those pieces together in a way that the job site can move much more quickly. And last, always collecting data so that we can improve and have a feedback loop to get better and better every time. So what I'm going to show you here is an example of the first piece of content that we've actually tried to use this process on. Really, what we're trying to do is build a process of thinking and of designing differently, and what we're focusing on is market rate multifamily projects as a first case study. So for us, here are some images of the places where people can live. We're very proud to say that we understand the difference between the user and the client. The user is the person that lives in these places. They're renters. They don't actually fund the making of the building, but we have to care very deeply about what they experience in the project, right? The amount of light, the amount of air, the amount of expression of natural materials, the use of the space. We have to, make this a great place to live, and so we want to make an aspirational place for people that they'll want to live there. But at the same time, our client is actually a developer who's got a different set of concerns. Of course, they want to be able to get high rents, of course. They want to be able to fund the project. But for them, being efficient and getting the most density on the site and being able to get the performer to work, those are the things that matter to that client. And so we have to address those issues as well. So what we try to do is marry those two worlds. And it comes down to really understanding the detail and the connections and the materiality and that kind of human touch for the renter and the user, but at the same time creating an efficient system for that owner. And for us as well, sustainability is a core feature. For us, it's important not just to be responsible, but to make that really come to life in the projects. And for us, it comes down to how is the carbon being used on the project. And we're really focused on both the operational carbon and pushing down that use of energy in the project as one uses it. But what we found a lot of success really in is this idea of pushing down the embodied carbon in the project. And our use of mass timber in the United States, as that's a growing new trend, we're able to really take advantage of that material and really push on a material that can be both amazingly expressive for a tenant, but also productive for the building, and make sure that we have a material that is able to be manufactured in a way that uses very little labor. It's very, very precise, and it is able to then sequester carbon in a way that concrete and steel are unable to at the moment. And for us, this makes a big difference to the embodied carbon footprint of the building and allows us to really make a difference as we come to the market there. So it starts with this idea of components. And what we want to do is break down that design into the smallest number of parts that as you relate them together and reuse them over and over again, they can combine to make many, many different unit typologies, building conditions. And so in the system that we've been working on, we've broken the design down to really just around 33 families of parts. And these families of parts come together in very predictable ways so that we can be able to understand the rules that they use to relate to each other, and then we can leverage that with technology. You can see here a number of the different unit types that can be made out of these same parts. The parts always have the same relationships, and as a result, it's a very rational system. And then once it's a rational system, we can then take advantage of that. It starts with really understanding everything possible about the component. Our components, for example, are much smaller than one would imagine. It's not volumetric modular. They're very small-scale pieces, like a column or a beam or a piece of millwork. The largest piece is maybe that bathroom pod, and it's the only volumetric piece. So we're really concerned about being able to ship things in a very efficient way, flat pack, from where they're created in the factory to the job site. But it's really important that we collect as much information about these pieces right from the start. We understand all of their dimensions, tolerances, their specifications, their points of connections, how the build material works, what is the labor that is involved to install of them, how many fasteners that are used, what is the timing it takes. And what we do is we take all of that data and we embed that right into the metadata of the BIM element itself. We also take this into a high level of integration and take that design down to a level of detail that doesn't often get applied to a project like a housing project, maybe to a more sophisticated performance type building. But for a housing project, this level of detail doesn't always come to pass. And so it's really important for us to segregate out how these pieces interact with each other, which pieces are made off-site, how they interact with pieces that are then built on-site, and we're really clear with the documentation that we deliver back to the people that are making the project. And then lastly for us, we try to take this level of coordination a step further. We take coordination to a constructability level of coordination. And this is unique, I think, especially in these kinds of projects in the United States, where one layers in not just the kind of design and engineering coordination that one expects from an architect or an engineer, but also layering in that level of constructability coordination that the general contractor is typically asking about. We want to take that information and bring it into the design process and ask those questions much earlier and integrate that much earlier into the process such that we can avoid mistakes or conflicts that then slow down the job site and actually make this then a kind of a problem on the job site. We want to predict where all these conflicts will happen such that we don't have them on the job site. So the first thing we did was we actually built a prototype of this system. We wanted to make sure that off-site we were able to predict not just in the computer where things were going to relate, but we wanted to see the real materials, how they were going to be installed, how many people it took to do the work, what were the fasteners, what was the process and the timing and the dependencies. And so we got the real materials from real vendors, and we built a one-bedroom unit inside of a factory. And we wanted to really test out, how long it takes, what's the cycle time, how many people. And really learn and gather that data before we got out into the real world so that we could then leverage that when we did. In addition to that, we are really into this idea of the technology replacing the brute force of creating these documents and these relationships. And so what you're seeing here is actually an illustration of what we call the unit configurator. Once you have the components, once you have the rules that govern those relationships, in that amount of time, before I could even get to it, it created the unit. And so this is not now drawing a unit, it's actually selecting the parts and telling the system what kind of unit you want. And then because we have these component parts and we understand the relationships, this unit is then formed in seconds as opposed to days or weeks. That allows us to then modify that as things change, as a component needs to be revised, or we find a better way of doing something or a less expensive version. We can then substitute out that component, run that configurator once again, and create a new version of that unit. Once we have the components and these units that we use as building blocks, we can then go through our process of putting them together to make a building. And this happens now very, very quickly. We can then assemble these units in a very, very lightweight way and use what we call our unit swapper. It's an add-on to the BIM technology to allow us to then just, with a click of a button, transform those conceptual units into highly detailed units within the project. In the first week or two of the project, we end up with something like this, which is a highly detailed version of the project, which is, for folks who are more attuned to this kind of levels of detail, it's the construction documents levels of detail. We're able to take this and turn this around very, very quickly. This productization allows us to know so much about the building very, very, very early in the process. It allows us to then test out the construction cost of the project, the sequencing and timing of the project before a developer gets too deep into the process itself. As a result, our documents can be outputted automatically in this kind of format where we're actually able to use data to drive a color coding system for the documents, which indicates which things are offsite fabricated versus which things are then built on the job site. So this helps the general contractor, the subcontractors understand the scope of work, what's their responsibility, what will come already made, and what then needs to be filled in on the gaps. And for us, this is a dynamic process. We're able to actually turn this on or off depending on each job site. So some job sites, some components might want to be offsite fabricated, but on other job sites, depending on the cost of the labor or the distance from the factory, it might want to be then built locally. So we then took this out into the world, and our first project became a prototype of how this system would come into practice. So very, very quickly, we identified a small site in Austin, Texas, and we started this process. Within the first 2 weeks of the process, we're able to actually get a full broken down bill of materials of the project and do bottoms-up estimates of the cost and the construction sequence because of the way that we're working. This is the typical construction sequence, the design and construction sequence that one would find in the world. And there's a lot of steps that then you have to do on every project that both the architect and the owner need to actually interface and reinvent that wheel every step of the way. So in the process that we have now going with this idea of components and with this idea of rules that drive this and this idea of systems that drive the automation of some of this effort, we can then screen out a lot of tasks that actually typically occur on a project. And the Juno process ends up looking like this. Much less numbers of phases, less intense phases, because we're leveraging a lot of that material that we've already started with. And so the net result ends up being something like you see here. We actually ended up having our documents finished about 60% faster than the conventional process because of leveraging that R&D, leveraging those tools. We then test the idea of a decentralized supply chain, having vendors across across the country, having competition for people making the same parts. We then will take that integration of the detailing that we start with. This, because we have a component, we can actually drill down into the detail very, very quickly. We can then translate that right into the factory. We can actually have quality control processes that actually go to the very fractions of inches and millimeters to make sure that this material is going to be exactly qualified and meet the standards that we need to by the time it gets to the job site. We can even do truck loading diagrams and make sure that the material is loaded onto the truck in the right sequence so that it can be taken right off the truck. And so then we end up with tools like this, which is really not a presentation drawing, but a working document. This allows us to work out the sequence of installation, the sequence of dependencies that's on the critical path of the project, and use this as a negotiation and a partnering tool with the crane operator so that we understood exactly what steps were going to happen, and we could understand what all the safety measures, the temporary supports, the number of fasteners, et cetera, in order for our project to know what was going to happen before it was meant to happen. So this level of planning is now able to be done before you get to the job site. In the interest of time, I'm going to skip. Okay, and then this is how the project actually went together. In just 5 weeks, we built the superstructure. And it was exactly to that plan. And we realized, actually, we could have even done it better. But because that level of planning occurred, we were able to actually be very predictive and very precise. And I'll point to this dumpster. You can see this little teeny dumpster, empty. Very little job site waste. As a result of this planning, there's nothing to be cut. There's nothing to be changed on the job site. We actually put that superstructure together with just 5 people, 4 men and a woman, in 5 weeks. And that's an amazing use of labor, and we're very proud of that. And that translation of the parts, that translation of the process actually paid off in spades. In addition to that, it's really quite critical for us to be collecting the data as the project is going together. So we have a number of tools and technologies that we took advantage of to make sure that we understood exactly which piece was picked, how many minutes it took of the crane, et cetera. We cataloged all of that information on data sheets. And I'll point out just here in this chart here, this is called an installation learning curve. And as the building went up, you can see the time it takes goes down because we're repeating the same processes over and over again, and people are getting better at their work. And this is a very, very small building. This is only 24 units, just a 5-story building. And as a result, we're seeing an amazing efficiency over just a small sample size. And so we think that if we can take these pieces and parts, this way of working, and apply that to many buildings, we can actually get better and better and better. The net result is a compression in both the time of design and also the time of assembly. And we think that this creates an efficiency that will actually make room for that level of quality we want to bring to people living there, to create a situation where we can create much higher quality outcomes in a much more efficient process. And so just to end, this is our project in Austin, Texas. It's just finishing now. Hopefully, we'll be opening that soon, and people can come see it. Thank you very much.